Hello and welcome back to Calculus 3, section 11.9 on curvature and normal vectors. So we start with remembering first the idea that we are going to use a lot in this lecture, and that is the idea of the unit vector. So we have to review that first. So unit vector with notation u with a hat is vector u divided by the magnitude of vector u. We said that the unit vector has the same direction as the original vector, and its length is 1. So the specs on the unit vector are magnitude is 1 and direction is the same as vector u. So this is something that you need to know from previous lectures to be able to survive this one. Now we are going to define something that is called unit tangent vector. From Calculus 1, I hope you remember that the tangent line was connected to the derivative, where the derivative was giving us the slope of the tangent line. That tangent line was the line that was perpendicular to the curvature of the function and was touching the function at exactly 1 point. We would say also kisses the function. So in Calculus 1, tangent line would be a line that touches the function at exactly 1, and it's perpendicular to the curvature like that. The best way to understand this would be obviously a circle, where in the circle, no matter where you draw the radius r, tangent line would be perpendicular. So that is the meaning when something is perpendicular to the curvature. Every curve that you can possibly imagine, doesn't matter, what it looks like. Every curve, okay, good. So you see that there is over here not much of rapid turning as it's happening over here, right? So that curvature, that's in the title of this lecture, we're going to learn how to measure, how to quantify this thing. But what it's important to understand is that every curve that you can possibly imagine, there is a big circle that would fit part of that curvature. So for instance, over here, I can draw a circle, and then there is a radius r, and then I can do the perpendicular tangent lines everywhere. So now what we know is that the Calculus 1 gives us the tangent line and the first derivative and all of that good stuff. So now, if I want the unit tangent vector, well, it better be found through the derivative of r, and it is. So we know that we are given r of t as a parametrization. I don't care whether you are talking about a 2D or a 3D. So it could have 2 or 3 of these, or 17, whatever. This can be done in any dimension. So we have the vector r, which is the collection of all parametric equations which parametricize the curve. If you use f and g, it's 2D. If you use fgh, it's 3D. Or you can use more if you need to. And then you have the derivative of this one, which would be simply f prime, g prime, and h prime. So now, so this is technically already a vector which shows the slope, right? So that is the tangent vector, but I need a unit tangent vector. So we are going to denote that with a t hat, because it's a unit vector, it gets a hat, not an arrow. You are not going to be wrong to put the arrow. Sure, you can put the arrow or the hat. It's just that we like to see the hat there because it signifies that it's a unit vector. and its equation must be, right, the vector divided by its magnitude. Now, since we are dealing with vector r, right, it's a function of t. So this over here is the unit tangent vector. Now, please observe the formula. Vector is divided by its magnitude, hence the word unit. It's the derivative, hence the tangent, and then it's a vector. So, right? So it makes sense to have these three words there. Now, we also know that vector r, of t in its parametrization form represents the path, all right? Or you can say the path is good enough. I like a road, right, which carries distance. And then the derivative of that in respect to time must be velocity then. So we know that r prime of t is actually v of t. So that helps me recast my formula into v's. So this could be v of t divided by the magnitude of v of t. And we know that the magnitude of v of t is what? Very good. So when you take the velocity and you divide it by a speed, all you get is the direction in which you are going. That's basically what it means. So you can think of the unit tangent vector either in terms of r's or in terms of v's, whatever makes you happy. Now I would like to move on to curvature. So we are going to measure curvature now. So in a nutshell, what's a curvature? It's how fast the line will turn. Now, does it have to be a line? No. Just think of a cable of some kind, right? And at any point of this cable, if the cable is not perfectly straight, which it's not, as you can see, this cable or the wire is going to make turns in space, and each turn has curvature which we can quantify through numbers. We are going to now develop the curvature equation, and that we are going to use that curvature equation to measure the curvature of the whatever lines in space. Now, these kind of lines and these kind of calculations are obviously important in designing mechanical devices and also designing, like structures and things like that. So you need to know about the curvature if you are going to make something nice, because generally things that are beautiful are not boxy. That's technically what it is. Right. When was the last time you looked at a Russian car and said, "Yeah, look at that, just a box"? So curves. Now, what is curvature? First, we are going to write the definition which will utilize parametrization through arc length. We can't compute things with that. It's only used to help us understand the concept. We are going to have a theorem which will give us a way to compute our curvature and other concepts that we'll do. So definition will utilize the parametrization through arc length. I'll explain more of it, but as I said, you will never use it to compute anything in that form. We are going to redo the equation and put it in a form that we can actually calculate. So let R, that's a vector R, describe a smooth parametricized curve. if S denotes the arc length, and T hat, which is R prime divided by magnitude of R prime, is the unit tangent vector. The curvature K of S is given by K of S is equal to the magnitude of dt of ds. Again, this is only going to be used for us to understand the concept. We cannot use it to compute things. So we'll take a look at the computational formula shortly. Let's just understand this first. So say I have some kind of curve, and I have in this area here curve that it's not turning as fast as in the area here. So curvature should be bigger here. Right, that's a bigger curvature, actually larger. How about that? Larger curvature, smaller curvature. So curvature simply measures how fast the line turns. Depending on what you have, you know, it could turn in 3D space, 4D, 7D, whatever amount of variables that you have. So now we have those curvature. Now, what are the concepts here? If I denote, let's go here and take just a small part of this function. So I'm going to highlight a small part of this function and say that that's my arc length S that I'm considering for curvature. Now, what I'm going to have here is the tangent vector. Say tangent vector goes this way, unit tangent vector. Unit tangent vector better be tangent at the point over there. So now, if you think about this, the derivative part in front of t is telling you how much it turns. If you studied the derivative and you know what it means, derivatives measure change. So I am measuring how fast is this tangent vector changing. Now, this is much easier observed on the curve that it's large, because the tangent vector over here, say it's this, over here is this, over here, right there. So you can see the tangent vector changing. This is all unit tangent vectors. All of these guys are unit tangent vectors. But they're computed at a different point, because unit tangent vector is a function, right? It's combination of all of those R's, parametric functions that are in R. So all of these tangent vectors will change in space as you progress on the arc length. So to understand the curvature, it simply says it's the change of the tangent vector as you go in respect to the arc length, which is what I have up there in pink. Maybe I should add that here as well. All right, so that's S. That's parameter, that's arc length S, and you can see that the unit tangent vector changes through that. So in respect to S, what is the change in the vector? The larger the change, the sharper the curve, the lesser the change, smaller the curve. Now, as I said, this is used only for us to understand how do we compute curvature. And as one of the important aspects. Well, we are going to do a slight mathematical manipulation to change our formula into a formula that is going to be used. So, curvature is going to be given as the absolute value of the change of t in respect to arc length s. So now what we can do is we can divide by dt. Right, so we divide by dt, and now what we have is ds dt, that's the velocity, right? So we have 1 over v dt dt.
Is it the magnitude of the velocity or just?
Yeah. Well, oh. Yep. Velocity is a vector. These are all vectors here. That's the vector. This is unit vector. So now I can write the curvature formula. So curvature, which is actually a function of time, clearly as you progress along the line, it's a different curvature for all of the lines that I that I drew earlier. So now we have 1 over v dt dt, or the better form, the one that we are going to use, is the derivative of t divided by r prime, because we know that's what velocity is. I mean speed with the absolute values. So what are you using for calculation? Out of the entire definition here, I mean theorem for computing, you are using this part over here. So use this to compute curvature. Now let's put some concepts together in our heads. Some kind of a path is given to you, and this path is explained through r of t. This path sits in some coordinate system. If we are using 2D, then it's sitting in a 2D coordinate system, x and the y. Specific location So specific location is happening at time t equals to a. And then there is a vector r computed at a, which stretches from 0, 0 to that point to show where the location of the particle or whatever it is that we're observing, to show where the location is. So it is parameter t that it's very important, because that t could be measuring in seconds, in minutes, in hours, in days, in months, in years, right? So you don't get any of the answers until you know at what time, right? If time is a parameter, or theta if angle is parameter, you want to know at what time, let's say, you are computing. So curvature is going to be the function of parameter t, and then when you say, okay, what's happening after 2 seconds? Great, t equals to 2, I can tell you the position of the particle, I can tell you the curvature of the path, because I would have the curvature computed, and I can just plug in t equals to 2 to find the curvature at that point. So you need to get used to this idea of location being presented as a vector, because remember, vector starts at 0, 0 origin, and it stretches to the point here. So this would be a vector 1, 2, 2.5, 2.5, 4.5, right? That's what the vector is. The way I drew that vector. So now if you have a vector 2.5, 4.5, that means that the point that it reaches is 2.5, 4.5. So this is the way you find location. This is what your GPS does. GPS, you have the satellite, right? And then that satellite looks down. Well, you have 3 satellites and stuff, but let's just simplify. Say that one satellite can do everything, right? So there's a satellite, and then it imposes the grid on the surface of the planet. Now, since the planet is huge, and one satellite cannot cover the entire planet, it just covers what's immediately underneath, you are looking at that patch of ground as a flat piece. It's finally flat Earth, right? And now you have the grid, right? And that grid is like the grid we see on a ceiling, and it has locations. So you can pinpoint every location simply on that grid. So everyone's location becomes the set of coordinate points, right? And then you decide the origin and where you're measuring from and all of these kind of things. So now, if you are observing from the sky, and this is a road on which the car is moving, and then there is some point of origin somewhere from where I'm measuring, this vector r will trace every single point along the road. So maybe this is, time equals 0, time equal 1, time equal 2, time equal 3, time equal 4. But then between time equal 2 and time equal 3, there are all other times in between that you can compute for. We just didn't care. But, time equals to whatever, 1 minute, 1 second, 1 hour, whatever you want to consider. So tracking location is as simple as telling me what time do you want to know, or location for which time you want to know, and I will plug that in R. How fast is the object moving? Well, plug that in the derivative, R prime. So fast is the speed. Figure out the magnitude. What is the direction? Aha, unit tangent vector. Unit tangent vector is going to give us the direction. Anytime the car spins out of control on a road, if there was any kind of spill or whatever, oil and leaves and stuff, the car is going to shoot off of the road in a unit tangent direction. That's what it's for. Unit tangent direction is going to give you that. If you spin something, let's make a projectile. Yeah. So, if you spin something and you let go,
oh my gosh.
I know. I don't have a stone yet. I have to get one. And if I let go, it is going to go perpendicular to the position. So if it was in this position, and I let go in this position, it's going to shoot forward because it was supposed to spin that way. So if I let go, this piece will just go straight because that's the tangential vector at that point. We've seen that last class when I drew that circle, and you guys know which way it goes. So you can trace the position, you can trace the speed, you can trace the direction in which it's moving, and now you can also calculate with this formula, you can calculate the curvature, you can describe it as a quantity, right? You can assign number 7 to it, and then you know that if next curve is 8, well, it's going to be sharper turn, right? So the larger the curvature, sharper the turn, lower the curvature, lower the turn. And then you can assign speed limits and things like this. I mean, there's just so much application to this that, you know, you can just think a little bit about it and you will see where it fits. So let's find the curvature of the circle. That would be the first thing to do. You have the formula, so I'll just give you the find the curvature of the circle of radius 6. R equals to 6. So you know that you are supposed to parametricize this, right, to get your R, and then figure out the rest of the ingredients that you need to find your stuff. So I'll give you the curvature formula on the board as well, so you can have the formula as well, and then you can do the parametrization and stuff. So you're looking to get a number at the end, like 7 or whatever you calculate, but you're looking for a number. How's the Calc2 going? We can all parametricize, right? R equals, and then you put the 2 parametric equations that describe the circle. What are those? R cosine x, comma R sine x. Very good. R is 6. Good. So R of t is 6 cosine t, comma 6 sine t. So that's our parametrization. Once you have R, you can get your R primes and tangent vector and
supposed to be the derivative of t on top, or is it just the other t? Because I have the long derivatives for some reason in my notes, but I don't know why. Yeah, isn't it supposed to be the unit vector over?
It's obviously the derivative.
Okay, well, we're just blind. It's okay.
No, that's okay.
Sorry about that.
That's fine. I mean, I have contacts myself, so I understand. Yes. Okay, let's take a look at this together. So you will have to know how to parametricize. That is in chapter 10, studied in Calculus 2 at RVCC. So deal with that. You have my lectures on it or whatever. When you have a circle, the parametrization for circle r of t is going to be, in this case, 6 cosine t, 6 sine t. Now, this can be switched. You can use sine first and cosine second, and all it does is it changes the direction of motion along the circle. So if you have cosine first, it's counterclockwise, and if you have sine first, it's going to be clockwise. That's the only thing that is changed. It's going to be the same circle. Depends only which one you push first. Now, clearly, in application, that's important, right? Which way the helix will spiral up? Is it going to spiral up this way, or it's going to spiral up that way, right? That's just a matter of what's first, sine or cosine. So once I have that, I can go and find r prime immediately, because we are going to need that, and that's going to be negative 6 sine t and then 6 cosine t. We also need tangent, unit tangent vector, which is r prime divided by its magnitude. So that's going to be negative 6 sine t, comma 6 cosine t, divided by the magnitude of this, and the magnitude is, when you square this, what do we get? 6. Right, so we get the negative 6 sine t squared plus 6 cosine t squared, and that just gives us, the whole thing gives us 6. So the unit tangent vector is simply negative sine t cosine t, because 6 is cancelled. Now I need the derivative of that vector, which is going to be negative cosine t, negative sine t. And then to find the curvature in respect to t, I'm going to divide the derivative, so the magnitude of the derivative. So negative cosine t, negative sine t, magnitude, divided by the magnitude of vector r prime, which is negative 6 sine t cos 6 cosine t. Top it gives us 1, bottom gives us 6, so the curvature is 1 over 6. Green? Good. Now please observe that the curvature is constant. Does that make sense? Hell yes. Why? It's a circle, exactly. So it's always this, yes, the same curvature around. It's not going to be the same for ellipse, right? Because ellipse, if you draw ellipse, right, it curves more here than it curves there. So it's not going to be the same for ellipse. So circle is this special. Now, can you make an argument? What is the curvature of a straight line? And now I'm going to be 5-year-old. Why?
Because it doesn't change.
Do the calculation. Yeah, because it's straight. Find the curvature of straight line. Go on. Let me add in R3. I know, terrible, right? You'll live. So now you have to know parameterization for this one, which is what we actually did in this class. Not today, but you learned parameterization of the line in 3D a few days ago. The answer is 0, yeah. It's common sense to be 0. I'm just, why? How? Where's your calculator? Where's the proof? This question could also say, prove that the curvature of the straight line is 0.
There's no, tangent vector. Tangent vector.
Write it down. See,
I don't.
yeah, I know. You're not writing it, rebel. Let's be the rebel.
Is this like a quick thing to prove?
Okay. Extremely quick. You just need to know parameterization for a line. I hope you do know. 0 over 0 doesn't necessarily have to be 0.
Wait. What?
No, why? You have the general form of the line. Imagine if there was a quiz today with that question, find the equation of the line, right? Everyone is rummaging through notes trying to find the most important definition. It is, but...
So that's right. Right, okay.
You need R, which is going to consist of 3 equations, sure, and then R prime, and then vector t and all of that kind of stuff.
Because the equation is going to be r equals 0, so then the derivative is 0.
Yeah.
Right?
So R of t.
No.
x0 plus at, very good. y0 plus bt and z0 plus ct. Great. So this is our parameterization. Vector r of t is going to be what? A, B, C. So now what? Unit tangent vector, which is when we divide this one by the magnitude, right? So what do we have? We have x0 plus at divided by the square root of a squared plus b squared plus c squared. That's the magnitude. Oh yeah, a. You're right. A over this, b over this, and c over this. Square root. A squared plus b squared plus c squared, and a squared plus b squared plus c squared. Do we all agree that these are just numbers? There are no t's anywhere, so this is all. So each one of these, let me write that in blood, each one of these is a constant. Each one of these is a constant. To find the curvature, you need the t prime. Exactly. And then when you divide zero vector by the magnitude of zero vector is 0 divided by the other magnitude is going to be 0. So that implies that curvature is 0. Good. Let's see what else we can discuss over here. You don't have to worry about the alternative curvature formula. I will write it, but I mean, some of you obviously, more ambitious than others, so you will. There's a cross product, v cross a, magnitude divided by the velocity cubed.
What would be the incentive to use one or the other? Like, in which situation is this a better equation to be using?
Depending what you're given. If you're given acceleration formula, right? If you give an acceleration vector, you have to integrate to get the velocity one, and then you have to integrate one more time to get r, and then go from there, right? So if you're given velocity and acceleration, you can just plug them in here, and these are vectors that we know, but again, this is specific. So alternate formula. For curvature at a point, and again, if you're given things, you can just use that. All right, so what else can we talk about? Principal unit normal vector. Principal, meaning we have to pick one that it's in charge, because there are multiple, and we'll see why and how. And then also unit, again, magnitude is 1. Normal hints of some kind of perpendicular orthogonal, so 90 degrees, and then the vector. So this guy is going to be perpendicular to the tangent vector. Why is this like every day at the same time? Why? I guess. So we are going to have, again, two definitions. One definition is going to be in the arc length parametrization, which is, again, not the way to compute things, just the way to understand things. And then we have the theorem, which redefines the whole thing as in terms of vectors that we actually compute. So let's start with the definition. Let R describe a smooth parametricized curve by arc length and the principal unit normal vector. So let R be a smooth parametricized curve by arc length. Then our normal vector, again there is a hat on it because it's a unit normal vector, is going to be the change in tangent vector divided by the magnitude of the change in the tangent vector, because we are looking for the unit normal. Now, if you haven't picked up so far, and I did tell you earlier that the tangent vector is perpendicular to the curvature, so when you are looking for a tangent line in Calculus 1, you always get the 90 degree. The tangent line is 90 degrees to the curvature. We don't discuss it, but you always do. And then also, you know that you cannot find the tangent line to the linear line, because that makes no sense, right? So when you have this situation now, it's layered again. You have vector r, which is just path. Then you have the tangent vector, which is perpendicular to that path at every point. And that was obtained through the derivative. Now if you take the derivative of the tangent vector, it will produce another vector that is 90 degrees to it, right? And all of these vectors represent, in the physical domain, they represent velocity acceleration if you want to think about that domain. So you have r to give you the path, tangent vector to give you velocity, and normal vector to give you acceleration of these things. So we see that the normal vector is just another derivative of the tangent. Now you had to take a whole bunch of derivatives to get to the normal tangent vector, right? You went the r and then you divided again. So now this is another layer. So these problems for normal vector can be very, very lengthy in calculations. So I also have to be very careful what to put on the exam. Now we're going to use the same trick, divide by dt, divide by dt, and we are going to get actually the formula which we are going to use to compute this, and that is going to be the derivative of the tangent vector divided by the magnitude of the derivative of the tangent vector. You can see that here because as soon as you have ds dt and ds dt, they will cancel. So the formula that we are going to use is going to say dt dt, divided by dt dt. Easier to write. It's the t prime divided by the magnitude of t prime. Now, this is a vector. Remember, curvature was a scalar. It's a number. We are quantifying curvature. But over here, this is a vector. So this is the formula which you are going to use to calculate. This is a vector. It's a unit vector. And vector is perpendicular to unit tangent vector. Now, because it's perpendicular to unit tangent vector, the common sense will tell us that the dot product between the normal and the tangent vector must be 0, because if you have two vectors that are perpendicular to each other, the dot product is 0. And principal unit normal vector points to the inside of the curve in a direction that the curve is turning. In the direction that the curve is turning. This is why parameterization is important. Now let's draw the situation from the circle one more time, and I will remind you that you have, when you start at the origin, you go out, and this red vector is vector r of t. Then let's go green. If orientation of the circle is this way, right, which means cosine first, you are going to have the unit tangent vector point up. At the point here. And you are also going to have in blue now normal vector point inwards. Now you've probably seen such a thing in physics many times, and now you hopefully understand why it's so. Now, for this part, in the direction that the curve is turning, you see that the turning happens this way. So clearly, if you have a path like that, this is out and this is in, because the curve is going this way. It will be actually the same if you did the other way, but this distinction is important for situations like this. Right? Now what's in, what's out? So if you are talking about this curvature here, this is out and this is in. But if you're talking about this curvature here, this is out and this is in. So you have to be careful, right? And I'm going to just put the directional motion this way, right? So you have to be a little bit careful about this. And again, this is going to come back in chapter 14 and going to come back with revenge. So you got to know these things for the parametrization. All right, so let's find normal vector for something. The rest of the section is application for physics to find the components of acceleration. So you don't have to worry about the rest. Let's get the example over here. We are sorry, but something went wrong, so you can't see your book. Okay, fine. Ah, there's the book. They have a very nice summary on page 851. I cannot make this any bigger because the software doesn't allow. If I use Control Plus, it just makes the size bigger. It's not making the text bigger. This is a summary of the entire thing: the position function, the velocity function, acceleration function, unit tangent vector principle, normal vector, curvature with alternative form, and then components of acceleration. We didn't cover these things, but you know they are available right there. So you can take a picture of this if you run out. If you want to have, I'm not sure if you have the book or not, but there's the entire thing summarized. I'll wait another 12 seconds if anyone needs to. You can post it on your Instagram too. Hashtag look at me. No? All right. that's that. Now let's take a look at some of the exercises. Components of acceleration. There is a normal vector. So 27 through 34. Let's choose anyone but you. So let's.
I think she's been scared away from herself.
27 to 34? 32? Too late.
I haven't even looked at it. What is it?
No!
It has been done.
What are we doing? Find the what?
Normal vector.
Yeah. Or 30.
Good luck.
Oh. Can you write them? Yeah.
Well, someone erased the board. No.
And we're just finding the unit, the principal unit.
Okay.
Right?
Right. Not sure what else you would like, but.
So we're going to have to remember all of these things?
Yes, this is your Calculus 3. The formulas, that's what you're learning. The rest of it, can you take the derivative of sine cubed? Right, that's Calc 1. So if I give you the formula, what are you doing then? You're doing Calc 1 derivatives. That's not Calc 3. So your job in this class is to know all the formulas because that's what the Calc 3 is. All of the calculations in this class are Calc 1. We're not going to do, trigonometric substitution and integration by, maybe integration by parts pops in once, but, I'm just going to leave the R prime there in case that you don't know chain rule from Calc 1. Just in case. Yes. You are looking for the normal vector. So my answer has to be vector. Normal. So you have to go past that point. You have to find the tangent vector, then take the derivative of that, and then divide that into the magnitude. Okay. So we clearly have to deal with the denominator, and as you can see, you can factor out 9 sine squared cosine squared. So if you factor out 9 sine squared t cosine squared t, if you factor that, what's left is cosine squared t plus sine squared t, and that's 1, right? And you can take the derivative of this. So it actually works out pretty well. -3 cosine squared t sine t, comma 3 sine squared t cosine t, divided by, all I have is 3 sine squared, sine t cosine t, because the square root kills the squares. So when you divide this, your vector t becomes 3 and 3 are cancelled, sine is cancelled, cosine is cancelled, so you just have negative cosine t. And then again, 3 and 3 are cancelled, sine is cancelled, cosine is cancelled, so just sine t. The derivative on this thingy is simply sine t cosine t, and then the normal vector is this vector sine t cosine t divided by its magnitude, which is clearly 1. So the answer that we are looking for is sine t cosine t. Cool, right? That was a good pick. Another one? Yeah, why not? What else are you going to do, right? I know how much you love logs, so I decided to pick the one that that has ln of cosine t.
Oh, thank you.
You're welcome. So same procedure. You have r, get r prime, get t prime, divided, and be done.
Those are like that. Yeah.
No, okay. Negative. I mean, yeah, so you take that and divide by 1, except magnitude that. Yeah. And then you. Oh, yeah, you have the magnitude of that. So you're going to face
Yes. Beautiful, huh? It starts with ln of cosine t, you know, few lines, gone. It's a little bit of Calc 1. Well, that's it. I hope you're not disappointed. Bye.